All right, we're back with part 6 of this Calc assignment. This is math from the void. How are you all doing? Math coming at you out of nowhere. So this one's going to be pretty brief. I've put out a video on domain and range in the past. I think mostly about domain, but covered domain and range and how to write this in interval form. But really, the key behind these problems, each one of these problems in particular, is being able to identify what type of function these are, and from that, being able to kind of figure out, well, what's the shape of the graph? So I really want to use this opportunity to connect the ideas of the domain and range, like the algebra that you know, and also the shape of these parent functions, which are going to be incredibly important, whether you're at pre-calculus level, algebra 2, or especially if you're in calculus. This needs to be your bread and butter by the time you're in calculus. So let's just quickly identify the type of function. This first one here, this is a quadratic function. And we know that the shape of a quadratic function comes from the parent graph x squared. So it's going to be a parabola. That's the name of the shape of the graph. Oops. Okay, we also know it's going to be downwards facing because we have this negative here. So it's going to be kind of like down like that. That gives us a clue about the domain and the range. We'll take a moment to analyze that more closely in just a moment. Let's look at the next function. This is a radical square root function. Okay, square root, and it has some transformations on it. We'll talk about what those transformations are. That's going to help us understand the domain and the range, because it's not just going to be the normal square root shape. It's going to be that basic shape, but it might not be facing the same direction as you see it. It might be flipped downwards, for example, or it might be flipped to the left. So these several, changes to the function here, the negative, we have 3 minus x, it's not just an x inside the square root, and the plus 5, those are all going to do some things to the graph that move it around and change its shape. You might know those as transformations. So again, we'll talk about that in just a moment. The log graph. If you don't remember, logs have a specific domain restriction, and they also have a specific shape to them, the logarithmic function. It looks similar to a square root graph, but in order to differentiate the two, I'm going to put the xy grid on the square root. Notice that it generally starts at 0, whereas the logarithmic graph has an asymptote, that's a boundary line at 0, and then it kind of goes through like that. So it does look similar. It makes sort of like a flattening out sort of shape to it. And actually the logarithm is much flatter than the square root. Put it something like that. So they look kind of similar, but they have different domains. They have different domain restrictions, and then these two are different functions. So of course they're going to have different little changes that are being done. We call those changes transformations. All right. Now let's talk about the domain. First one's easy. The first one is very easy. We don't need to graph the exact function in order to get the domain and range, but it just helps to have the picture of the graph. So let's kind of put this on there and see what it can tell us. If we put this on a graph, what is the function's shape going to tell us? That's this thing here, by the way, right? What is this going to tell us? In fact, maybe I can make it all one piece so that it moves together. I know that it's upside down. There we go. That's good enough. What this is going to tell us is it's going to tell us how high up the graph goes. Right? If I put it up here, then it has a high y value. If I put it down here, it has a negative maximum value. So depending on where this is at, depending on how high up this is, That's going to determine our range. But we can safely say right now that the range is going to be from negative infinity all the way down at the bottom to some value. That's the maximum. So wherever the maximum is on this parabola, the vertex you might call it. So if we can find out where that vertex is, we can find out this point. That's the y value that we're looking for, like literally from this highest point on the parabola. That's what's going to go there. So how do we find this highest point? This comes down to being able to find the maximum of a, let's see, weird. I don't think my text box is working. So that comes down to being able to find the maximum of a quadratic function. Here we have a quadratic function in ax squared plus bx plus c format. What we need to do to find the vertex location is we could complete the square. That is one possibility. Another possibility is just to directly solve for this maximum with two steps. Step one, we're going to find the axis of symmetry. And the way that we do that is we use this formula, x equals negative b over 2a. So here we're going to have x equals negative 6 over 2 times negative 1. And so this is going to be 6 over negative 2 or negative 3. Now that is the x value. That's step one. Step two is to plug in the x value in order to get the y value, which is going to be where the maximum happens. So what does the negative 3 tell us? The negative 3, it tells us where the vertex is on the x-axis. So that's going to be like right here. So that's approximately at negative 3. Now let's find the y value, because the y value is the maximum value. That's this line here. How do we find a y value? We plug in x values. So simply y equals negative, plug in your x equals negative 3, minus 6 times negative 3. And then what is that, plus 4? Yeah, plus 4. Okay, so we have negative in front of a negative 3 squared, which is 9. You understand that? There's a negative in front of the parentheses. And that's because in the equation it's negative in front of the x squared. Okay, so this is going to be negative 9 plus 18, 6 times 3, and then plus 4. So this gives us 13. So that is the y value here. It's up at 13. I know it's not drawn to scale. If this is 3, if this is negative 3, that definitely doesn't look like it's a 13 up there, but you get the idea. So the range is going from negative infinity to 13. The range is the set of y values, and this parabola is going downwards forever. I know I drew the arrows right there, but it's going down forever. Okay, now what about the domain? I'll give you a second to think about the domain. There's a reason why I haven't mentioned the domain, because the domain is very easy. It's all real numbers. You can write it like this, or you can write the interval from negative infinity to infinity. Either way, that's kind of an ugly infinity. Sloppy. There we go. Either way, that is your domain. How do I know all real numbers? Well, remember the domain is the set of x values which are represented by the function. In other words, the x values that you're allowed to plug in. And a polynomial like this doesn't have any restrictions. There's no rule that you're breaking if you plug in a negative, or if you plug in 0, or if you plug in a fraction, or any kind of number. As long as you plug in a real number, there's no issue. We can't say the same thing for a square root. We can't say the same thing for a fraction. We've talked about rational functions in this very calc prep assignment. So a polynomial, which a quadratic is an example of, it's a degree 2 polynomial. Any polynomial x cubed or x to the fourth or x to the fifth, any of those. They have no domain restriction. They allow all numbers, all real numbers, from negative infinity to infinity. And if you look at that on a graph, the connection to a graph is that this function is going to keep going to the left and it's going to keep going to the right. Even though it's going downwards, it's going steeply downwards, it's still technically going a little bit to the left always. Even when it looks like it's going vertical, it's still going to go all the way to the left. And it's going to continue going very far down very quickly as it's going to the left and the right. Okay? I hope that explains that. Now let's take a look at the square root. The square root has several transformations on it. And we know, especially if you watched my video on the domain, we know that the square root function has a restriction. What's the restriction? The inside here needs to be non-negative. So that means that 3 minus x, that's the inside of the square root, needs to be greater than or equal to 0, and it will not be negative. So what does that mean? If we just add x on both sides, that means x is less than or equal to 3. Or you could say 3 is greater than or equal to x. That's how it looks right now. So because of that, if we look at a number line, x needs to be less than or equal to 3. Here's 3. It can be equal to 3 or less. And so how are we going to write our domain? That is perfectly acceptable for our domain. Or if we want it in an interval notation, we're going to say from negative infinity, comma, 3 with a bracket. Okay, it was pretty easy to sort that out. So what does this tell us about the function? Oh, right, I don't have my text box ability, so I'm going to have to say this out loud, and you can write it down. I'm also going to write it in notated format, like on the whiteboard with the pen, but I'd rather type it out if possible. The idea is that this tells us the function f of x basically goes left. And I'll put goes in quotation marks. The reason why I can say that confidently is that it goes left is because on the right side there's a hard endpoint, so that's like a boundary that it actually reaches. It's like a starting point. And on the left side, it goes towards negative infinity. But of course it's never going to get to negative infinity. It's just going to keep going down. So in a sense, it sort of goes left. That helps me understand what the drawing is going to look like. And that's what the domain tells us. It tells us what's going on with the function, like on a left to right or right to left basis, horizontally. Now let's look at these transformations and take those into consideration. This negative in front, y'all know what that does? Same thing that this negative did, which is it reflects across the x-axis. Sorry, it's a little blurry. It was a really small picture, and I enlarged it a lot, so I guess it got kind of blurry when I enlarged it so much. And the inside here, this is a reflection over the y-axis, because if we factor the negative out, so I'm going to put reflects across the x-axis and the y-axis. The y-axis is from the negative that's on the x, and the x-axis reflection is from negative that's on the outside, so this one out here. We also have a shift by 3 units to the right. So we're going to shift to the right by 3 from like the starting point, which would be 0, 0, by the way. See how I have the parent function kind of sketched out here? And then this plus 5 is going to cause us to shift it up 5. So what is that kind of going to look like? That way we can identify the range here. Well, I'm going to go up 5 and to the right by 3. Maybe I'll make the unit smaller than that. 1, 2, 3. 1, 2, 3, 4, 5. That's where the new vertex is at. Just from the shifts, you understand? Just from the shifts 3 and 5. Haven't reflected it. So if I didn't reflect it, it would look something like this. And the range would therefore go from 5 up to positive infinity. But in fact, I need to reflect this. I need to reflect it across the x and across the y. So that's going to send it down and to the left. Which means that the range at its lowest, even though it looks like it's flattening out, it's going to keep going downwards. It's just going to be going very far to the left. From the lowest, it's going to hit negative infinity. Well, it's not going to hit it, but you get what I mean. It's going towards it. Even though it looks like it's going flat, at some point it's going to keep going down so far, further than anything else. It's never going to stop going down. And the highest point that it reaches, and it does reach it, so it has a bracket, is 5. And so there's our range. There's our graph, and there's our range. Okay? Again, feel free to pause the video at any moment, like before you're doing this one, and see if you can remember what domain is. If you can't remember what the domain is for log, maybe you should watch a different video first. Watch the video on watch my video on domain. I have a decent one that covers the domain restrictions that you'll be worried about. Okay, let's take a look at logarithm. So, what's the domain of a logarithm? We have some transformations, but we'll talk about those in a minute. The domain on a logarithm is that the inside, also called the argument of a logarithm, the inside must be greater than 0, not just greater than or equal to, but greater than 0, which means, of course, x must be greater than, not greater than or equal to, it must be greater than 4, strictly greater. We can draw that on a number line. There's 4. We're not allowed to be at 4, but we can be greater than 4. So then the domain is going to be 4 with a parentheses, and it's going larger towards infinity. So that right off the bat tells us that instead of our graph starting right here at the boundary of 0, it's going to start at like 4. So it's going to have to get, moved over, of course. All right, so let's draw a grid for that. What's special about the range of the logarithm? Let's look at the parent function of the logarithm to investigate that. The logarithm goes all the way down to negative infinity, and it technically continues increasing. Logistic growth is slow but steady. It is always increasing. So it covers full range. So some takeaways, which I'll put notes on these other parent functions here. This one doesn't have any specific openness like this. Range is all real numbers, but the quadratic does. The quadratic, we have that the domain is always going to be all real numbers, or if you want to call it, maybe I'll just, instead of all real numbers, I'll put negative infinity to infinity. There we go. So that's always true, no matter what quadratic you're dealing with, no matter what logarithmic you're dealing with, the range will be negative infinity to infinity. Okay, let's talk about the transformations though, because this transformation is going to flip things. This is going to reflect across the x. Oops. Across the x-axis. Okay, this is going to shift things. These shifts are going to happen. This is shift 4 to the right, which makes sense because we just looked at the domain and we saw that the asymptote is going to get shifted 4 to the right. It's also going to go up by 1. So we might as well talk about the special point of a logarithm, the parent function of a logarithm. That special point is 1, 0. Special point for a square root, the normal sort of vertex or starting point, if you want to call it that, is 0, 0. That's the special point. And then when we move things around like we did, it's going to start at a different spot. This one's now at 3, 5. Well, our special point 1, 0 is going to get shifted, what do you say, 4 to the right and 1 up. Which means instead of crossing at 1, 0, we're now going to cross at 5, comma 1. Like that is an exact point that we know for sure. And what's more is that we know that the asymptote is at positive 4. Now, the reflection is going to cause the thing to be flipped, though, upside down. So instead of going like this, it's going to go upside down, more like that. And if we wanted to solve for this 0 point, we actually could. So let's do that. It's a little bonus question that we got here. Let's solve for this x-intercept. How do we find an x-intercept? This is a great exercise to just know how to do all the time. We set y equal to 0, which means we set the whole function equal to 0. So negative log base 2 of x minus 4 plus 1 equals 0. This is negative right now, so move it to the other side, and we're going to get that 1 is log base 2 of x minus 4. And we can change to the exponential form. This means that 2 to the 1 power is going to be equal to x minus 4, which means 2 equals x minus 4, and therefore x equals 6. So that gives us the exact value. It looks like it's a nice whole number there. That's where it crosses the x-axis. Okay, so this is 6, 0. Alrighty guys, that'll do it for today. It's just a quick recap on how to use domain restrictions and also some transformations of functions in order to graph and determine the range of those functions. See you next time.